Before I want to go on, I just want to give you a brief warning about exponentiation notation. Sometimes we're talking about languages and the characters look like numbers, right? So depending on context, 2 to the power 3 could mean different things. If 2 is a number, 2 to the third power is just 8, because it's 2 times 2 times 2. Whereas if 2 is a character, 2 to the 3 means 3 copies of 2 all concatenated together, giving you the string 222. Similarly, if 15 is a number, 15 squared is 225. If 15 is a string, 15 squared is 1515. So be careful to not mix these things up, right? Or you always be careful from context, whether you're talking about 2 the number or 2 the string. Okay? With that in mind, I'm going to start talking about the language of a DFA. So as a reminder, the extended transition function n star takes a state and takes a string and returns a new state that you live in after reading that entire string. The word language just means a set of strings. So for example, the set 0, 1 and 0, 0, 1, this is a language, just a collection of strings. We say a string alpha is accepted by a DFA if from the start state S0 and you read alpha, you end up in a final state. So how we can formally write that using the extended transition function is that n star of S0, when you read alpha, that this thing here is going to be some new state. That new state has to be an element of F. And what was F? F was the set of all final states, because there could be more than one. So this statement here is the same as this block of English here, right? That's just how you formally write it. Now the language of some DFA A is precisely the set of all strings that it accepts. And we denote the language of a DFA A as L of A. So L of A is the set of all strings made out of the alphabet of that DFA, so all W and sigma star, such that from the starting state, if I read W, I end up in the final. I end up in one of the possibly more than one final states. So we call that the language of a DFA A. And if a DFA A has the property that its language, the language of A is equal to some set E, so E is the language of A, we say that A recognizes the set E, or A recognizes the language E. Okay, so that's what recognizes mean. And our goal in this section of the course usually is to, given a DFA, we want to describe its language, so formally write out what's the set of all strings it accepts, or given a set of strings B, so given a language B, find a DFA that recognizes B. So I got some examples here for you to work through, and in the next video I'll do the solutions. So here I've given you a DFA. I want to know what the language of this DFA is. So see if you can find, work out for yourself what the set of all strings is, if you can find some sort of succinct description that describes describes all but only the strings that are accepted. And create a DFA yourself that recognizes this language here. So the language here, L, is any binary string W, so any string of bits 0s and 1s, such that, I've left a step here, such that this thing equals W, such that W is equal to a 1, followed by n many zeros, followed by a 1, where n is strictly greater than 0. So this set here is going to be equal to the set 1, 0, 1, or 1, 2 zeros and a 1, or 1 and 3 zeros and 1, or and so on. So it's going to be an infinite set. So see if you can create a DFA that recognizes this language.